Okay, good afternoon, everyone. Let's get started with our lecture number 10. So, till now we looked at the overall RF integrator, RF systems. We looked at some very general principles. We looked at nonlinearity, we looked at noise, and we developed metrics for each of them. We looked at sensitivity, dynamic range, and so on. So now we are kind of stepping into the circuit domain. Okay, so this lecture is on passive impedance transformation networks. Okay, now let's review some very basic RLC networks because they are going to kind of form the foundations for this particular topic. Okay, now I'm sure all of you are very familiar with the series RLC and parallel RLC circuits, right? So let's just quickly brush up our memory on that, right? So a series RLC circuit will look something like this, correct? What is the resonant frequency? Come on, guys.
1 by 2 pi root LC.
Correct. Why do you have a doubt?
No.
Okay. So yeah, so many of these things we learn in your second year or something, and there's a tendency to forget these things. So that's why we are just brushing up these basics. Okay. So a parallel RLC network will also look something like this. Correct. Okay. Now what will be this resonant frequency? Same, right? So when you have an LC network of this sort, you basically have the same resonant frequency. It's 1 by 2 pi root of LC. Okay. So here between these 2 points, if you look at the Z, okay, the impedance can be written as what? R plus j omega L plus 1 over j omega C. In other words, it can be written as R plus j times omega L minus 1 by omega C, right? At resonance, what happens? At resonance, this term goes to 0, right? And so Z0 becomes R. Okay. Similarly, for the parallel RLC, what happens? The Y, it's easy to write it in terms of Y, which is the admittance. Admittance can be written as G plus j omega C plus 1 by j omega L, right? And this can also be written as G plus J times omega C plus 1 by omega L, right? And this term becomes 0 at resonance. Okay. So if you plot the Z versus frequency, the magnitude of Z versus frequency for the series. Oops, what did I do? Okay. So for the series case, and let's say the magnitude of Y versus or rather the magnitude of Y versus frequency. So this is for the series RLC. How will this curve look like? The impedance is given by R plus j into omega L minus 1 by omega C, right? So if you take the magnitude response, which is root of R squared plus the imaginary term squared, right? How will this look like?
Upward
will
parabola.
This have a minimum? Sorry, yeah.
Upward parabola, sir.
It will be an upward parabola, or rather, kind of, probably not a parabola, maybe a hyperbola. I don't know. Okay, it will be something like this. Correct. So this is your F0, where Z becomes the minimum at Z0 equal to R. And at other frequencies, what happens? For lower frequencies, the capacitive impedance dominates, and at higher frequencies, the inductive impedance dominates. Correct. Basically, the crossover point is your resonance point, right? Here R plus j omega L will be very low for low frequencies. 1 over j omega c term will be very high for low frequencies. So it is capacitively dominated, right? This whole network is and pretty much an RC network at low frequencies, and at higher frequencies it's pretty much like an RL network where the inductor is dominating the response. Okay, the impedance is dominated by the inductance. Of course, the time domain response and all is very much, it's not like an RL or an RC. It's a, all of us have studied the second order response given by this series RLC, right? Now, if you look at the parallel RLC, what happens? You again get the same thing. The impedance goes to the admittance goes to a minima at the resonance frequency, and at lower frequencies, what is going to dominate? What is going to dominate the inductance? Dominate the admittance? Inductor or the capacitor?
Inductor.
Inductor. Inductor is going to dominate the admittance term, and at higher frequencies, the capacitance is going to dominate, right? So if we plot the magnitude of y will also be something like this, where this is basically your G, right? Now, many times we are more interested in the Z, right? So if you plot the magnitude of Z across frequency for a parallel RLC, how will it look like? How will this curve look like? Will it still have this shape, a V-type shape, or it will be an inverted? It will have the inverted,
sir.
Right? So this is how your resonance will be basically be, right? And this value will be equal to R. Okay. So in many of the, so if you take a parallel RLC, right, the impedance at resonance is equal to the value of the resistance. Same thing in series, but it reaches a minima for a series, maxima for a parallel RLC. Okay, magnitude of this has a minima at f0 for series RLC and a maxima at f0 for a parallel RLC. Okay, so this is something that we should understand very clearly. Now, I am sure all of you are familiar with the notion of Q, right? By definition, Q is omega times energy stored divided by energy average power dissipated, right? There are different versions of the same formula, right? And you can calculate it, and let me just give you the final expression. Those of you who want to convince yourself, please refer to either network analysis by Haight or any of the network analysis book, or even the textbook might have a derivation, or you can easily find it on the internet. So in the interest of time, so for the series RLC and the parallel RLC, so these are things that all of us have already studied. Okay, the Q is given as what? Omega naught L by R, which is also given by 1 by omega naught RC, which is also given by 1 by R root of L by C. So if you get one of the expressions, you can always get the other expression, right? You just substitute for omega naught, or you substitute just basic algebraic manipulation, you end up with this, right? So omega naught L by R or omega naught RC is equal to 1 by R root of L by C. Whereas for a parallel RLC, basically it is the exact inverse, right? You have R divided by omega naught L, or which is equal to omega naught RC. This is also equal to R root of C by L. Okay. So, and another important thing is basically here the current through a series RLC is the same, right? But the voltages across the things VL and VC can be different. Whereas here the voltage is the same, the current IL and IC and IR will be different. Okay. So how are they related? Let's take the series RLC for example. At resonance, how can you write VL as a function of the other voltage?
Q into V.
Correct. So if there is V is given, V naught is given by I naught times R at resonance. Okay. Uh, Basically, this is V naught is nothing but VR. VL can be written as what? Q times V naught. Okay. And VC will be minus Q times V naught. So basically, the magnitude of VL, of course, this is a time varying thing. So the magnitude of VL and VC is Q times V naught, but VL will be negative of VC. So if VL is positive, VC will be negative. If VC is positive, VL will be negative, right? Same way for parallel RLC, what happens? Let's say I naught is equal to the current through the resistor, which is equal to, let's say, V divided by R. Okay. But IL, magnitude of IL will be equal to the magnitude of the capacitor current, which will be equal to what? Q times the I naught, right? And again here, IL will be opposite in direction to IC. So as in resonance, what happens is the overall voltage across the two terminals will still be equal to I times R, right? Or I naught times R, the current at resonance. But the voltage across inductor and the capacitor will be very high and they will be in opposite polarity, cancelling out each other. Whereas for a parallel RLC, the voltage is constant because all three are in parallel, but the current through the inductor and the current through the capacitor will be Q times the current through the resistor, right? And the proof is very simple. You can just write what is IL equal to V divided by Z, and then you can expand on Z, and you'll easily get the whatever we are talking about. Okay, the proof is very simple. You can attempt it on your own. Okay, and this is what you basically get. Okay, the proof is like you write IL is nothing but, let's say, V divided by Z. What is the Z for L? You substitute, collect the terms, and you'll basically get the thing. So far I hope all of you have understood. These are very crucial things. In fact, in LNA design, we will use some of these concepts. Okay, we exploit some of these concepts. Okay. Now the other thing is, in general, we talk about bandwidth. Now, how is bandwidth and Q related? Let's, instead of equality, you tell me, is it directly proportional to Q or inversely proportional to Q?
So inversely?
Inversely, sir.
It is inversely proportional to Q, right? So that is like if you look at, let's say, for a parallel RLC, the magnitude of Z versus F, it's going to look like this, right? So if you have a, let's say, a low Q system, your low Q system will be like this, right? And your 3 dB bandwidth, right? So your 3 dB bandwidth will be much wider, right? So let's say this is bandwidth 1 and this is bandwidth 2, right? So bandwidth 2 is greater than bandwidth 1, where Q2 is lesser than Q1. Okay, same center frequency, same resistance there, right? So which is why the peak is the same, but then if your Qs are different, you'll have wider bandwidth. So low Q systems have higher bandwidth and high Q systems have very narrow bandwidth. In fact, you'll have a very peaked response. High peaking means basically means high Q, basically means lower bandwidth, and vice versa. Okay, and bandwidth and Q are related by omega naught by Q. All right. So again, the proof for this is also quite simple. Some of the textbooks on network analysis will have these things. Basically, you just write it at around resonant frequency, you just add a small delta W or delta omega, and then you find out what is the delta omega at which the magnitude goes to 1 by root 2 of the response, and then you find that out, and that turns out to be something like this. So this is a very important relationship, which says bandwidth is given by the center frequency by Q. So here you will get bandwidth in terms of radians. If you want bandwidth in terms of hertz, it's basically F naught by Q. All right. Okay. Now with these basics being refreshed in our memory, let us now start attempting how to build impedance transformation networks. Okay. Now, why do we need impedance transformation networks? What is the necessity?
For matching.
For matching, right? So we all know that whenever some part of your circuit is going to interact with your outside world, let's say this is your chip boundary, okay? Let's say your LNA is sitting inside here, and let's say you have an antenna off chip, right? Now what happens is this routing is long. The length of this L is comparable, or is either comparable or greater than lambda. Okay. So which means that you need to match your input. Zn has to be equal to the characteristic impedance Z0, typically which is around 50 ohms. Right. So now the input impedance of your LNA has to be 50 ohms. Same way, if you say, let's say you have a power amplifier, let's say this is the chip boundary, this has to drive your antenna. The dimensions inside the chip are very, very small, as we discussed in one of, I think, the first class. But here again, the length is comparable to lambda or greater than lambda. Right? So what will happen? You have to again match this output impedance to 50 ohms. Right? So you need some matching network, and also as we start looking at power amplifiers and so on, we will see that there is a necessity to kind of down convert that impedance in order to be able to deliver the power and so on. Okay. So whatever all said and done, there are impedances which are not equal to 50 ohm, which need to be changed. Okay. Either you up convert the impedance or you down convert the impedance. Okay. Now how to do it using passive networks is what we are going to see today. Okay. Now we looked at very standard forms of parallel RLC and series RLC networks. Okay. Now what happens if you have a network which is basically okay, before we go into it, let's look at what is called as series to parallel and parallel to series conversion. Okay. That is to say, let's say I have a series resistor RS and a C. Okay. I want an equivalent circuit which is going to be like this. I have a parallel C and some, let's say, C dash and RP. Okay. Now how can you convert between these two? This is a series RC network and the other one is a parallel RC network. Now how will you convert between these two? Okay. So let us write equations. So we know that between these two terminals the impedance is the same, right? Between these two terminals the impedance is the same. It's only the representation here that is changing. Please understand. Okay. Between terminals, let's say 1 and 2, you have a certain impedance which can be expressed as either a series combination of R plus JX something, or it can be expressed as a parallel combination. The admittance can be expressed as G plus some JY. Okay. Now how do you go back and forth between these two? Okay. So in order to do that, it's very simple. You just equate the impedances of the two. What is the impedance here? It is RS plus 1 over J omega C, which should be equal to the impedance between, let's say, the same two terminals. What is the impedance here? It's a parallel combination. So it becomes RP into 1 over J omega C dash, and it is RP plus 1 over J omega C dash. Okay. Or instead of writing dashes, let me just say it is CP, makes life a little easier. Okay. So if these two networks are equivalent, then the impedance seen between the two terminals have to be equal. Okay. So the right hand side expression can be written as what? Rp divided by 1 plus j omega R Cp. Correct. Or you can also write it in terms of S if you want, but that's okay. Right. Now let's equate the real and imaginary parts. In order to do that, we have to rationalize the two sides, right? And what should we do? Rp into 1 minus j omega R Cp divided by 1 minus omega squared or 1 plus omega squared R Cp, R squared C squared P, right? Now let's equate the real part and let's equate the imaginary part. Okay. Now if you equate the real part, what happens? Rs is equal to Rp divided by, what do you have? 1 plus omega squared Rp squared Cp squared, right? Now is this term familiar, omega Rcp? What is that?
One by Q.
It is Q, right? Like, so for a, if you look at a parallel RLC, right? So what happens is basically you basically get Rp is equal to, or rather Rs is equal to, this is Q squared. So this is the, one second, what did we have here? So this is Rp, right? Okay. Right. So Rp divided by 1 plus Qp squared. Correct? Because for a parallel RLC network, the Q is omega Rc, right? And, or in other words, you can also say it is, yeah. So this is how you write. So Rs and Rp are related by 1 by Qp squared, and if Qp squared is much greater than 1, it can be written as Rp by Qp squared. Okay. Now typically, now the thing is, now you might ask a question. Okay, in this network we are talking about only an R and a C, but where did you get Q from? Didn't we talk about Q in context of RLC circuits? Okay, so that is a question that many students will definitely get, so which is definitely a very valid one. Okay, now, okay, I think I made some mistake here. Okay, that's okay. I think we can, yeah. Now, basically what happens is, if you have a parallel, any RC circuit or an RL circuit, okay, the notion of a Q for an RC circuit or an RL circuit is that you assume there is an appropriate inductor tuning the capacitor out at that frequency. Okay, if you assume that there is an LP here which is tuning out the capacitor at that frequency, what will be the Q of the circuit? Okay, so that is the way Q is defined for even RC circuits or RL circuits. So have that in mind, don't get confused. Even if you have only two elements, or for that matter on the right hand side, left hand side, you have a series RC network, right? So the Q of the series RC network is given with the same formula if you assume an imaginary inductor which is kind of resonating out the capacitor. If that is the case, what will be the Q expression? So you use the same Q expression. Okay, basically here you write an expression which involves only R and C. Okay, so that is how we write this. Okay, and typically for both circuits the Q will be the same. You can't say you know, the Q is different for both the things, right? So it will be like this. So the Rp is going to be like this, and Cp, I'm just writing the equation here. So you'll have Q squared divided by Q squared plus 1 into Cs. Okay, so you can derive the thing. So you have the imaginary part here, also you have the imaginary part. So both sides you have minus j, So the sign gets cancelled. So 1 by omega c is equal to omega rpcp divided by this 1 plus q squared form. Okay. So this can be written as basically this same way. Okay. So these are very important expressions, right? So this Cp for a sufficiently higher value of Q can be written as almost equal to Cf. So which is why when you go from series to parallel and parallel to series, the capacitor remains the same, or even for that matter, the inductor remains the same. You can do the same analysis with an inductor also, and you'll get the same results. The reactive elements remain the same, but the resistances are scaled by the factor of Q squared. Okay, or to be more exact, Q squared plus 1. Now, exploiting this fact, let us try to look at it. Now, look at this particular expression. Rs is given by Rp divided by Q squared plus 1. Okay, so in the textbook you will have Qs and Qp. The notion is that Qs is equal to Qp because the Q cannot change because it's essentially the same impedance, same network. Okay, it's just that the series becomes parallel and parallel becomes series. So Qs is equal to Qp. So you can just use both interchangeably. Okay, all right. Now here, so what happens is if you look at this expression, you can see that by converting from one form to the other, you have a change in the resistance value. So for example, let's say Rp is 50 ohm and let me say Q is equal to 2. Okay. Now what will be Rs? Rs will be basically 10 ohm. In other words, if I put a capacitor in series with, let's say this is 50 ohm and this is some capacitor value C, right? If I look at this particular thing, this becomes Rs of 10 ohm plus minus some Jx. Correct? Is this making sense? I am putting a capacitor in parallel with a resistor. Okay, and if I look at it, and if I want to look at the series impedance here, the series impedance is what? It is scaled down by a factor of Q squared plus 1. Okay. Now, if I want to get rid of this minus Jx part, all I need to do is just add an inductor here, right? So that this is equal to plus Jx. Now what will happen? If you add the inductor, all you will have is basically 10 ohms. Is this clear? Is this making sense? Right? It's a very, very interesting way of doing things. It's a very simple but a powerful way. You know that when you go from parallel to series, you have reduction in impedance, right? Or when you go from series to parallel, you have an increase in impedance. Here I wanted to down convert 50 ohm to 10 ohm. All I did was I put a capacitor in parallel to that, and I know that that can be expressed when you put something in parallel. We know that at any frequency, the capacitor will, I mean, when you have two elements in parallel, the effective impedance is reducing. And we know that if you do it with a Q factor of 2, it's going to come down to 10 ohm minus 10 minus J some X. And you add an inductor which has a plus Jx here, so that you have only 10 ohm. Okay, this type of matching is what is called as an L match. Is this clear? Are there any questions? Okay, so for an L match, you can always write that the series resistance seen here is nothing but Rp into Q divided by. So let me just write it in a more generic way. A more generic way of doing is to say Ls, and you have C and Rp. Now looking from here, Rs is nothing but Rp divided by Q squared plus 1. Okay, and the Ls and C are basically tuned out at that particular frequency. Okay, at F0, J omega Ls is equal to 1 by j omega c. Okay, because c is almost equal to this thing, or you can write this is q squared into q squared plus 1. Okay. Now this is one type of L match, and this is also called as a low pass type match. Okay, because this arrangement of L and a C is basically a low pass way of doing things, right? You can also do the same thing using inverting the L and the C. That is also possible. Okay, that becomes a high pass L match. Okay, there is also one more, that is basically you can get something like RP, L and C. This is a high pass way of using an L match. Okay. Now both these circuits are basically down converting impedance. Okay. This is for down converting RP to RS. Okay. Or it can also be thought of as up converting RS to RP. Okay. These are all passive networks, so they are bidirectional, right? So which means that if you have some resistance RS here, let's say RS, L and C, here if you see, you will get RP, which is equal to Q squared plus 1 times RS. Got it? So this is the same network. If you look from the other side, you basically get an up conversion in impedance. So in other words, you can also design a network such that if you have a certain RS, you can put an L in series with it, and you put a capacitor across it, and you'll basically get RP, which is like that. The other way to do it is also to say the high pass network RS, C and L. So again you'll get RP. RP being equal to Q squared plus 1 times RS. So this is the L match network is bidirectional in nature, right? You can take, if you put an RP, you will get a lower RS, or if you have a certain RS, you will have a higher RP. Depending on which direction you want to go, you can basically use this network, and the relationship between RP and RS is Q squared plus 1. And if your Q is sufficiently high, you can approximately say it is Q squared. There are two implementations. You can have a low pass implementation, or you can even have a high pass implementation. Okay, depending on what you want to have at very low frequencies and very high frequencies. Okay, is this clear? The L match network. Any doubts? Any questions? Okay, all right. So I am assuming that there are no questions. Okay, now here let me give you a problem. Okay, now the overall Q of the network, right? See, if you have a if you take this particular case, the Q of this RC or the Q of this RL, right? If you want to, okay, let me take a new slide. Now, what is the Q of this whole network? The Q of this network can be written as either, this is a parallel RC, so you can say omega naught C times RP, or you can also say it is, looking from here, you are having RS and it is a series network, so it is omega naught L divided by RS. Okay, and it turns out that both will be equivalent. Okay, because RP and RS are related with Q squared plus 1. Okay, and so basically, if the disadvantage with this L match network is that if you need a certain transformation ratio, that fixes the Q of your entire network. You understand? Like if you want, let's say, I want this 50 ohm to be down converted to, let's say, 5 ohm, then you calculate the Q that you require. Let's say, let's take this example problem. Like, let's say I want 50 ohm to be down converted to 5 ohm. Then what will you say? Okay, RP divided by Q squared plus 1 is equal to your RS. Okay, So this is nothing by 50 is equal to 5. 50 by q squared plus 1 is 5, which means what is q? Q is nothing but 10 minus 1, 9, q is equal to 3. Correct. Now your transform, this is the impedance transformation ratio. Okay. So what happens here is the impedance transformation ratio is basically setting the Q of your overall network. Let's say for example, you are designing a power amplifier, you want this down conversion, but you also want this to be a very tight filter, which means that you want the bandwidth to be very small. You want a higher bandwidth, higher Q network. Okay. But you cannot achieve it because if you set the Q based on the impedance transformation ratio, the Q of the overall network is already set. Okay. So that is the disadvantage. The Q is, you have only 1 degree of freedom. Okay. Or rather, it's called as 2 degrees of freedom. That is basically, you cannot, for a given omega naught Rp by Rs ratio and Q, only 2 can be fixed. Okay. Your Q is limited by the Rp by Rs ratio or the impedance transformation ratio. That is, for a given, if you want to set it for a particular center frequency and Rp by Rs ratio, you have to live with whatever Q you want. Or if you want Rp by, if you want the Q and if you want the omega naught, then you have to live with whatever Rp by Rs ratio that you get. Okay. So people said we want 1 more degree of freedom. Okay. How to have, the question now becomes how to have a network, how to design a network that gives you flexibility in both Q and the impedance transformation ratio. Okay, that is the question. So here enter 2 different networks. There are actually a few more networks also. One is called as a pi match network. Its dual is a T match network, and then we can also have what is called as tapped capacitor or tapped inductor networks. Okay, so in today's class, okay, we are already coming close to the end of the class. Probably I'll just introduce the pi match network, and the T match network is basically just a dual of it. Maybe in the next class I'll just touch upon that and we'll move to LNS. Okay. Now for a pi match network, all of us know what is a pi, right? What is a pi type network? So let's say you have a low pass type pi, which is basically you have C1, C2 and a L. Okay. So let's say you have a certain Rp here, you will get a certain Rin here. Okay, and vice versa. Okay. So this is what is called as a pi match network. The dual, obviously you know that you can also have this is a low pass pi, obviously because you have capacitor to ground and series inductor. The high pass network pi, high pass pi will be basically like this. You will have C, L1 and L2. Typically what happens is, of course, this is a high pass. Now typically we want to have lesser number of inductors because inductors occupy a very large area on the chip. So any topology which gives you the least number of inductors is always very much preferred. Okay. Now the way to analyze this pi network is like this. This pi network can be decomposed into 2 L match networks. Okay. This L itself is decomposed into, let's say, L1 and L2. Okay. And this is, let's say, C1 and C2. Okay. Now you have what? You have 2 L networks. So this L network will take this Rp, and you have an intermediate resistance Ri. Okay, intermediate resistance Ri is lesser than Rp, and this Rin will be greater than Ri. Okay, so this Rp is down converted to a lower value, and this lower value is up converted to a little higher value Rin. Okay, so now because you have these three elements, you can independently set the Q of the network and the center frequency and the impedance transformation network that you basically need. Okay, so what I will do is I will stop the class here, and in the next class we will just continue with pi match network and see how we can design a pi match network and T match networks and tapped capacitor network. And after that, we will, the second half of next class, we will move over to LNA design. Okay. Now, is there any question, any doubt?
Sir,
Yeah.
sir, I have a doubt from the previous portions.
Okay.
Sir, in the flicker noise expression, you
Okay.
taught that it is K by WL into COX into F.
Yeah.
So if I reduce the gate width, W decreases, and so the flicker noise will increase.
Yes.
But on the other hand, if I decrease the width of the gate, the
Yeah.
RG resistances, the corresponding RG resistance will also decrease, which is spreaded over the gate width. So
Correct.
the resistance, the number of, if the number of resistance is decreased, so the ultimate noise generated by the gate resistance will also decrease.
Correct.
So these two aren't they contradicting each other?
Yeah.
On one case it is decreasing, and the other case it is increasing.
Yeah. Welcome to the world of circuits. That's how it is. Okay. So this is where, or rather, I would say, this is the world of engineering, right? So in engineering, we always have trade-offs. Okay. So these trade-offs will definitely, so this is what you pointed out is a very classic example of trade-off. You increase the area, the flicker noise reduces. But if you increase W, you increase area, which means, area is money in the semiconductor world. Okay, sometimes they occupy a larger area, and the parasitic capacitances and other things will also increase, right? And as you pointed out, gate resistance will increase and other things. Okay, so there is always a trade-off between opposing quantities, and in each design, you take an engineering decision and you say, okay, this is the limit, I will live with this. Suppose your flicker noise is getting very critical for your particular design, you optimize it such that you have, little lesser flicker noise, but you live with little more gate noise and, other things. Thankfully, in RF circuits, unless you are working with oscillators and things like that, the flicker noise does not directly come and affect you. Of course, in mixers, oscillators, and so on, there is, in mixers especially, there is an up conversion of the flicker noise. So there you will have to optimize for flicker noise. So there is always a trade-off. That's how, life, that's how circuits are. Or in general, that's how practical systems are. You always have a trade-off.
Okay, sir. Thank you.
Okay, so any other questions? All right, so let's wind up today's class with this. Thanks everyone. Have a nice day.
Thank you, sir.